So we're going to talk about Riemann sums. This is just a review of things that you should clearly already know, but we're going to go over them anyway. So this is from geometry. An area of a rectangle, shouldn't have to even review this, but we're going to say it's width times height. So width times height, we multiply this by this, and that's our area. For a trapezoid, if you remember, it's width times the average of the two heights. So we can either say height 1 times height 2 over, sorry, that's not a times, that's a plus. Height 1 plus height 2 over 2. So we average these two heights together. We can think about it as just if this is 5 and this is 7, we just say 6 times the width. Or we can average them first, add them together, then divide by 2, then multiply by the width. So let's look at an example of that. And that's, again, another mistake. But, okay, so now we have a rectangle here. This is 5 times 10, which is 50. The area of this trapezoid would be 5 times the average of these two. So this is 6 and 8. We can just say the middle of them is 7. So we do 7 times 5 is 35. Or we can say 6 plus 8 is 14. Divided by 2 is 7. And that's 5 times 7, which is 35. Up to you how you want to think about it. But it's the average of these two. Okay? So that's what we need to know for Riemann sums. Now, what's the actual question? So let's look at this function. This is y equals 4, which is just going to be a regular horizontal line. And the question, when we're talking about Riemann sums, is we wanted to know what is the area under the curve. So we haven't done this yet, and it's going to come up as definite integrals. Happens to be, what do you know? This is the definite integral, which we haven't done yet. So I don't want you to, worry about looking at that and seeing those complicated examples. And we're going to see in Riemann sums, I'll show you in the next few slides. You don't need to know this yet. Just ignore this notation for now. But I want you to understand what they're asking for. So I know we're skipping ahead because we haven't done definite integrals yet. I'll do it when I come back. But Riemann sums is like a topic by itself. So I wanted you guys to do one topic while I'm gone. So Riemann sums, the question is, what is the area under the curve? That means the area from the function itself to the x-axis. So that's the question. What is the area of this green box? Let's say I'm looking at from 0 to 5, from x equals 0 to x equals 5. That's our question. What is the area? So this is very simple. This is a rectangle, right? So we're going to do 5. 0 to 5 is 5. That's the width. And the height is 0 to 4. So it's 4 times 5. So the area of this function is just 20. The area under the curve of y equals 4 from 0 to 5 equals 20. Turns out it's just a definite integral, which I know we haven't said definite integral yet. It's the integral with numbers on it. We're not going to deal with how we find that, with math. We're just dealing right now with a Riemann sum. So when we talk about Riemann sums, we're drawing rectangles or trapezoids or triangles to find an area graphically, not algebraically. So here is very simple. It's 20. Let's look at another example. It's a little bit more complicated. This is the function y equals x. So this is this blue line up here. And the question now, I could ask the same question. What's the total area under the curve from 0 to 5? So we're talking about the area of this blue triangle. So we can think about this two ways. It's either a triangle or it's a trapezoid. A triangle, you guys know, the area of a triangle is going to be half base times height, right? So we can look at this and say, okay, the base is, again, 0 to 5, which is 5. The height is 0 to 5, right, which is also 5. So we have a 5 times 5 over 2. That's 25 over 2. So we can say the total area here is 12 and a half, which is 25 over 2, by looking at the area of a triangle. Or we can say this is the area of a trapezoid. How do we say it's a trapezoid? Well, this is just 0. So this height is 0. So we say it's the width, which is 5, times the average of the two heights. So the height here is 5. The height here is 0. That's 5 plus 0, which is 5, over 2, it's 2.5. That's somewhere here, right? That's the midpoint. So we say it's 5 times 2.5. It's the same thing as 12.5 or 25 over 2. You get the same answer. Here, it's probably simpler to think of it as a triangle, because if you don't like thinking of a trapezoid with 0 height. But let's look at one more example, which is more complicated, where we use Riemann sums. Look at this function, y equals x squared over 10 plus 2. Here, it's much more complicated, right? We don't know how to find this area very simply. We don't have an equation to find the area from 0 to 5 here. So we need to use something called a Riemann sum. It's this guy named Riemann. It's an easy question, so you should be thankful for him. Like L'Hopital, he helps you, okay? And this is going to be almost always a question on the free response. So it's an easy question. It's always the same, pretty much. So we'll learn how to do it. Now we have a couple of different types of Riemann sums. So there's different methods we can use. The most common is left, right, and midpoint. We're going to talk about a trapezoid one also, but it doesn't really come up on the AP so much. I've seen it a couple of times. I can pretty much bet that you won't have a trapezoidal Riemann sum. It might show up on a test. It's probably not going to show up on your AP, but we're going to go over it anyway. So the first method we call is the left Riemann sum. What does that mean? We're going to break this up into different sections. So if I look at this graph, right, I can, instead of like we said before, finding one rectangle, I can sort of break this up into multiple rectangles, right? And approximate it. So I can almost make, if you see what I'm doing here, I'm making a bunch of rectangles, right? And right now I'm not using a left-hand Riemann sum. I'm just drawing arbitrary rectangles. But what a left-hand Riemann sum does is the following. Let's say I break this up into a total of 5 intervals, okay? So if you can see, I'm using 0 to 5. I'm breaking it up. Let me center them and drop more. Ignore the heights of them right now because we're going to adjust that now. But if I take this and I break this up into 5 different rectangles, and why 5? Just because I chose it. I can break this up into 50. I can break it up into 2. It doesn't make a difference. The question will always tell you how many intervals to use. So I'm breaking them up from 0 to 1, 1 to 2, 2 to 3, 3 to 4, and 4 to 5. 5 different rectangles. If I now add up all of these rectangles, I get an estimate, right, for the total area. See how this is close to that red shape that we had before? It's not exact, and the point of Riemann sums is it's close. Now, obviously, if I make a lot more rectangles, we'll look at an example now on Desmos, which lets us slide and use a slider to see how many rectangles, but we'll get closer and closer. We'll see that in a minute. But a left-hand Riemann sum says the following. Look at your interval from 0 to 1 and use only, right, we have two y values. We have the y value at 0 and we have the y value at 1. Left hand, obviously by the name, we're going to use the value on the left, which means we use this point. See this point right here? That means we come up to this point of the function on the left side of this boundary, and we make that the height of the rectangle. So you see how it's below the function here, but here it touches it. The same thing for this, we're going to use the left point. Here we're going to use the left point, touches the graph on the left, here touches the graph on the left, and here touches the graph on the left. So now what we can do is we add up every single one of these rectangles by getting the value of the function. So here it's 2, here it's, we don't know what it is, 2.1, we can plug it in here. 2.3, 2.9, and 3.5. So we do 1 times 2 plus 1 times 2.1 plus 1 times whatever, so on and so forth. Add them all up, and we get an approximation for this area under the curve. Now, another question they can ask you with Riemann sums, is it an overestimate or an underestimate? They're only going to ask you this on left and right, and when it's very, very easy to see. So here we very clearly see, right, we're missing some of the red area. So we know this is going to be an underestimate, meaning the actual area under the curve, this, right, is bigger than our estimate because we only used the purple. We're missing all this red. So if we got, for example, we got an answer of 3.792, the actual area could be 4.12. So it would be less than the actual area. So they wouldn't ask you what the actual area is yet. That would be an integral problem. But they could ask you for the area of a Riemann sum and tell you, is it greater or less than the actual area under the curve. Now let's look at a right Riemann sum. So a right Riemann sum, just like a left Riemann sum, is going to be very similar, but instead of using the left point, we're going to use the right endpoint. So look at the right side of the boundary. We come up till here, right? And we can do the same thing for the next interval, but we're going to come up till here, to this right side, and up till here, and up till here. And the good part about the Riemann sums is usually in these questions, they give you all the data points. So you don't need to find anything by plugging it in. And usually they're calculator questions. So yes, in the worksheet that I'm giving you, you can use your calculator. If you didn't have your calculator, go get your phone. You could use it. It's just adding up normal numbers. So here we would do the same thing. We would multiply 1 times this plus 1. And why am I using 1? Because it's 1 to 2 is 1, right? Every width here of the rectangles is 1. multiplied by the height. We add them up all together. Here we can see it's an overestimate because we have this extra green area on top, which is bigger than the total area under the curve. So here we would say in this case, a right Riemann sum is an overestimate. It doesn't necessarily always mean that a left is going to be an underestimate and a right is an overestimate. It depends on what the function is doing. So here, since the function is concave up, happens to be that a right hand will give us an overestimate, and a left hand will give us an underestimate. But if we had another example like this, where it comes down and it's concave down, it would be the complete opposite. The left hand would be an overestimate, and right hand would be an underestimate. You don't need to always think about overestimate, underestimate for the concavity. If you remember when we used linear approximations, we just had to think about concavity. We said the U is concave up is an underestimate. Here, you're always going to have a visual representation of it, so you'll be able to just look and see. Okay, so it's a little bit easier. The other thing which we didn't discuss yet was a midpoint Riemann sum. So a midpoint Riemann sum, this is a little bit more complicated, but instead of taking the left point and the right point, I'm going to take the middle point. Now what this means is not the middle of the two heights, that's the trapezoid. So let me say that again. We're not looking for the average of the two height points. We're taking the height at the middle. Okay, this is where everyone gets a little bit confused. A midpoint Riemann sum is still a rectangle. I'm going to say it again. A midpoint Riemann sum is still a rectangle. Do not draw a trapezoid. That's the biggest mistake people make in Riemann sums. Midpoint, we take the height at the middle, not the middle of the heights. So we're going to take this, and we use this point right here. You see this point at 1/2. What is the height? Now, it could be the middle. It could be the average between the height here and the height here, but it doesn't always have to be the case. We're still drawing a rectangle. Here, we would take the middle. Here, we would take the middle. Here, we take the middle. And here, we take the middle. And we'll look at an example of why it's so easy to calculate midpoint Riemann sums is you know in the question what they're asking you to do. You won't get confused with trapezoids, and I'll show you why as an example from an actual free response question. Okay, that takes care of midpoint Riemann sums. For trapezoidal Riemann sums, it's a little bit different because, give me 1 second. Okay, here's an example of what we would do for trapezoidal. We're going to take a trapezoid from the left and the right height. So we're going to go like this. We're going to go like this. We come up here, draw a trapezoid, and finish it off. Okay, so you see how we have a trapezoid like this, and we would go again, another trapezoid here, another trapezoid here, another trapezoid here. We're taking this point and this point, making a trapezoid. Now we would have to do a lot more math. It's not complicated, it's just more math because we're going to have to say, okay, this point is 2.9 plus 3.5, average them together, divide right and divide by 2, then multiply by 1. Do the same thing again and again and again and add them all up. Let's look at an example of a trapezoid with one more little caveat, which is, up until now, we've been saying, okay, make intervals that are all 1 unit width, right? I would say, okay, I want the area from 0 to 9, so make 9 separate rectangles or 9 separate trapezoids. And say 0 to 1 is 1, 1, 1. The width was always 1. Here, they're different subintervals. We call this a subinterval. So here we have only 3 subintervals, right? 0 to 1, 1 to 4, and 4 to 9. We have trapezoids, so we know it's a trapezoidal rule. But the widths of the subintervals are different. Now, you're not going to have to make this up. The question is going to tell you the subintervals to use. But the second most common mistake is not to realize that the widths of the subintervals are different. So here, look, this width is 1. This width is 1, 2, 3. This width is 4 to 9 is 5. So we would say 1 times the average between 1 and 2, which is 1.5. The height at 1/2 is also 1.5. Here, the midpoint height would be this on the black line, but the trapezoidal average would be on the red line. So they're slightly different here. This is when midpoint and trapezoid Riemann sums are a little bit different. So that's what I was saying before. Don't get confused. So but going back to what I was saying before, the width here would be 1. The width here would be 3. So this would be 3 times 2 plus 3 over 2, which is 2.5, right? And we would do 4 plus 9. I'm sorry, 9 minus 4 is 5. So that's 5 times 3 plus 4 over 2. And I'm not doing the math here because we're going to do a bunch of math. You'll do it with Ronnie now. But just want you to understand the difference there, okay? The last thing I wanted to look at is just 2 free response questions for the wording So number one here, if we look up here, right away they're giving you a table of data, right? So you don't need to actually find anything from the function in this question. It's very nice and easy. They're giving you, this is the x values and these are the y values. So these are going to be your heights that you're going to use, and the widths you're going to say, okay, so I want, look what they're telling you. This is the question right here. Use a right Riemann sum. Always. They're always going to say the word Riemann sum, or estimate using subintervals. It's very clear and easy what they're asking for. What I want you to ignore for now is to approximate this integral with these numbers. We didn't talk about this yet, and you don't need to know this. We will get to this. I'm skipping out of order because I didn't want you guys to do definite integrals while I'm gone. I wanted to be there for that. So ignore this, and I don't need you to explain the meaning of this. Okay, there's no reason for you to do this yet. This is fundamental theorem. We don't need to talk about this. I just want you to focus on the right Riemann sum. And two things to note. So number one, if we look here between the subintervals, look, 0 to 2, that's an interval of 2. But here, 2 to 5, that's an interval of 3. This is back to 2, 7 to 11 is 4, and 11 to 12 is 1. So here, the width of the intervals are all different. Here it's 2, here it's 3, here it's 2. So just keep that in mind when you're writing your widths. You need to double check. Most of the time it will be the same, but here it's not. Okay? The second thing is they're using a right Riemann sum. So when we're saying 0 to 2, we have the height at 0, which is 5.7, and we have the y value at 2, which is 4. So clearly for a right Riemann sum, we're going to use the one at the right side of this interval. So from in this rectangle, right, that goes from 0 to 2, where you're going to use this 4 value. In this rectangle that goes from 2 to 5, we're going to use this 2 value. We're only looking at the one on the right. If we looked at the one on the left, we would be doing a left Riemann sum. If we looked at the average of these, so 2 and 4, we average them together to get 3, we would be doing a midpoint Riemann sum. Sorry, I said it myself. I said it wrong. I did the exact mistake I told you guys not to do. If we look at the middle of the heights, we get a trapezoid because we're taking two heights and averaging them together. We cannot do a midpoint Riemann sum here. We don't have the value between these two, right? We would have to take the middle between 2 and 5 is 3.5. I don't have the y value at 3.5. I don't know what it is. It doesn't have to be between 2 and 4. It doesn't have to be 3. At 3.5, it could be anything. I don't know what the function looks like. I'm not able to do a midpoint Riemann sum here, and I don't need to because they're telling me to use the right. But in another example, let's look at the second thing. Approximate blah, blah, blah with a Riemann sum using the midpoints of 5 subintervals of equal length. So here we're using equal width, right? But the key here is they want a midpoint Riemann sum. Almost always for a midpoint Riemann sum, they're going to give you so many more points than you need. So you see how they only want 5 subintervals? That means you only technically have to give me 5 jumps. Look how many I have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They gave me 10, which is double. That's the key. Almost always for a midpoint Riemann sum, they're going to give you way more points than you need. And you'll say, why do I need to do that? Because my first subinterval is going to be from 0 to 10. I'm going to take the middle of that subinterval, which is 5, and look at the y value there. So even though your width is going to be 10, 10, 10, 10, and 10, we're only looking at the height at 5, which is 12. So this is going to be 10 times 12, plus 10 times 30, plus 10 times 70, and so on and so forth, right? So in the rectangle situation, it would look like this. We're using 10 times the middle point, plus only the rectangle, because it's midpoint, it's rectangle, times the middle, plus a rectangle times the middle, and so on and so forth. To show you one more thing, this is a Decimos example. I didn't make this example, but it's great. It's like an interactive thing that you can play around with. And here we have the same function that we've been talking about in the beginning, where we have x squared over 10 plus 2. So this is this function here. And here you can see they're doing a left Riemann sum, right? They're making 1, 2, 3, 4, 5 subintervals, and they're using the left point. But look what I can do. Look how nice this is. I can take this c value and I move it. Look what happens. Move it here, and now it's a right Riemann sum. You can see the difference between a left and a right, and also a midpoint. So this is a midpoint Riemann sum, where they're literally taking this. This doesn't show a trapezoid or Riemann sum, but we only have left, right, midpoint. And I want to show you one more thing. I can also adjust the number of intervals. And notice one very important thing, which we're going to get to when we do definite integrals again, and limits and all that stuff. But if I adjust how many subintervals, see how I'm moving this, the width of the rectangles are getting much narrower, but also what else is happening? My area under the curve is getting more and more accurate, right? So the more rectangles I put, the closer I get to the actual area. So this is begging us to say, take the limit as the number of subintervals go to infinity. That's going to be an important concept when we're talking about integrals, but just notice that as we increase the number of intervals, we get closer and closer to that. Okay? And that's pretty much it.